Now let's look at the change of coordinate systems. So we've already seen how do we represent coordinate systems in frames. We've seen if you add a point to a coordinate system, we get a frame. Now, suppose we have two different representations. We have the coordinate system, one using one set of bases and another using another set of bases. Now we have to go from one coordinate system to another coordinate system. So basically what we have to do is we have to apply a transformation on the corresponding vectors. So what we mean here is we have A, which is represented by alpha 1, alpha 2, alpha 3 transpose, and B, which is represented by beta 1, beta 2, beta 3 transpose. So we have to somehow connect between A and B. Okay. Now, suppose we have a vector W. W can be expressed in terms of a basis v1, v2, v3 as alpha 1, alpha 2 in times v1, v2, v3 transpose. Similarly, if you have another basis v1, u2, u3, this can be represented as beta 1, beta 2, beta 3 into u1, u2, u3 transpose. So, the way to go here is since v1, v2, v3 is a basis, all the vectors, the basis of the other basis u1, u2, u3, all these vectors can be represented using the earlier basis which we have. So u1 can be represented as a linear combination of v1, v2, v3. ut can be expressed as another linear combination, and u3 can be expressed as another linear combination. And we can always write this in terms of a matrix where M is equal to, we put all the coefficients of u1 together, u2 together, and u3 together. Similarly, we stack it up all together to give this matrix. So the representations are related. This is A, remember this is A, and this is B. These two representations are related by A is equal to M transpose B. Okay, so this is how they are related. So if you have B, if you have A, then if you have B, then the way to go to A is apply M transpose over it. Similarly, this is for vectors, which we have seen. Similarly, we can also look at points. How do we do change of basis here? So similarly, if we have A as a point in one frame and B as the point in another frame, all these vectors can be expressed. The basis vectors as well as a point in the second frame can be expressed as the linear combination of the basis of the first frame and the point in the first frame. So here, what we have to notice is that while we are writing the point in terms of the first point and the basis, only in that case we have the P0. So in all other cases, P0 is equal to 0. So matrix here will be a 4x4 matrix, where the last column of the matrix will be 0, 0, 0, and 1. Here also, how we are relating A and B is by A is equal to M transpose B. So this linear transformations is equivalent to, whenever we are applying a linear transformation, it is equivalent to change in frames. And affine transformation is actually a subset of the linear transformation. So it's a subset of all possible 14 plus 14 linear transformations. If we are so if you see here, we have a 4x4 matrix, but for affine transformations, these we're considering. Right now we have only these 12 makes a difference, but the last one does not matter. So only 12 degrees of freedom because the final column of the matrix is fixed. So this is the affine transformation which we are performing. And additionally, these transformations preserve lines. So we don't have to take care about uh, the lines because it's already preserved under these transformations. So in OpenGL, normally we have a world coordinate system and a camera. We have a world frame and a camera frame to be more precise. The base frame is the world frame, and we can then represent the entities in the camera frame as well. So we have to change the world representation to the camera representation using a transformation matrix. So initially, we assume that the word and camera frames are actually coinciding. So the transformation matrix is identity. But there are cases where if you look at this sort of setting, you get objects on both sides of the camera, which is not actually desirable because whenever you're looking at placing a camera, we just want the objects to be only on one side of the camera. So how do we do this? This can be done rather than if the objects are on both, you move the camera frame. So basically, you have to move the camera by a distance t on the z axis. So we look more into. So what will happen? Even though this is an identity matrix initially, we have to apply some sort of translation, that minus t, uh, uh, to move the camera by a distance d in the z-axis. We'll look at these transformations in more detail in the coming lectures. Okay, so let's end this discussion here.